Okay, so the idea now is to try to use the Jensens inequality for concave functions for proving the upper bound for entropy of a random variable. Let's call it x. So I want to get an upper bound for the entropy of a random variable x using the Jensens inequality. So let's just have a general look at the Jensens inequality in general. I won't get into the details, and then use the formula for entropy and try to get an upper bound for its value. So the Jensens inequality, it states that if I take the sum over ai f of xi, it less than or equals the f of the sum of ai xi inside, when ai is greater than 0 and the sum of ai is 1, and we are talking about a range of I and f is concave. Also, we know that the sum, or let's say okay, so now the entropy of a random variable can be written as minus the sum of pi log on the base of 2 of pi. This can be written as the sum of pi log on the base of 2 pi, and I can take the minus here, log calculations, so it's in minus 1. So I can write it also as sum of pi log on the base of 2 on 1 over pi. This I can say is less than or equal based on Jensens inequality. And why can I use it? Because log on the base of 2 is a concave function. You can take the second derivative and get, I think that it is always concave. Okay, so I can say that this equals the log on the base of 2 of pi times 1 pi. Oh, I forgot the sum. Pi, yes, like this. Of course, from I to n. So what is written here is just, we can do like this, right? So this is log on the base of 2 of the sum of 1, I to n. So it's log on the base of 2 of n. And this is the real result. The entropy of a random variable is always less than or equal this value, and it equals it when all the values of the random variable are equal. I can even write it just like this. So, or I can take 0, 1. When they are all equal, and here it is, should be 1 over, oh no, if I'm talking about p, so I can say that in this case p0 equals p1 equals pn, and it equals 1 over n. In this case there is an equality, but generally I showed you the inequality, the upper bound for the entropy of a random variable using the Jensens inequality, because log on the base of 2 is a concave function, okay? Therefore I can use this Jensens inequality to show what is the upper bound on entropy of a random variable, and the equality holds only when all the probabilities for each value of xi equals, in this case, 1 over n, because we have n variables. And you can think about it like drawing a, I don't know, like coin. So for each option, if the coin is not biased, for each option there are two options, and for each option there is probability of 1 over 2, half. So it is the case in which the probabilities all equal. So it will hold that the entropy for this case, for drawing a coin, is the entropy for this is, think about it, is half times log on the base of 2 of half, in minus here, minus half log 2 of half. This is the entropy, right? So if you think of this value, this is half plus half, and you get 1. And this is exactly log on the base of 2, and because n here is, we have two options, so it's log on the base of 2 of 2, which is 1. And we got exactly what we said, that for the case of coin, because every probability equals the other one, and each probability just equal 1 over n, and in the case of coin there is only two options, so it's 1 over 2, and we really got what we said, the upper bound for the entropy, which is log on the base of 2 of n, which is log on the base of 2 of 2 in the case of coin, so it is 1. So here we showed an example of how we can show that it really holds this inequality and equality in the case of all the probabilities equal. Thank you very much. So this was using the Jensens inequality to showing the upper bound for entropy of a random variable, and that's it.